Our next presenter is actually an alumni of our program. One of the great things about the way our Salk Scholars program is set up is that the students will often come in during their sophomore, usually at their summer after their junior year, as Brandon did. But then because they can come back the summer after their senior year, we often get students who will spend 2 summers with us, and Tamara is a great example of that. So this is Tamara's second year in our program. We were extremely excited that her lab wanted her back. That was very cool. She just graduated from Scripps Ranch High School and will be attending UCSD in the fall, which I absolutely love because that means we get to keep her. So I'm sure we'll see her back here again, working in her lab. That's one of the other great things with our program is that many of our alumni, after they leave the Scholars Program, continue to work in the labs throughout their undergraduate years. So I actually have quite a few students on campus. As a matter of fact, I've got a couple of them sitting in the back. Hello. So that's one of the great things about this program is it really does build a continuity with the science. She plans to major in physiology and neuroscience, which she got into working in her labs here, probably going into medical oncology. And one of my favorite things with Tamara this year was really seeing her emerge as a leader with the student program. So thank you for all your help that you've done. Tamara.
Hello, everybody. My name is Tamara Zubatiy. This summer, I worked at the Computational Neurobiology Lab here at the Salk Institute under my mentor, Dr. Ryan Rokamp, and my PI, Dr. Tatiana Sharpie. My project is called Analyzing Neurons of Different Auditory Areas Using the Maximally Informative Dimensions. The Computational Neurobiology Lab is a very interesting place. We study how might neurons encode information. So how does our brain recreate the world around us internally? We do this by studying sensory data. And the reason that we study sensory processing is that because it can provide us with quantitative data that we can actually break down and study numerically. So, yeah. And then another aspect of our lab is we do modeling to try to figure out how neurons encode information. And we do this by running statistics and various algorithms on stimuli and on responses to try to figure out how our brain encodes the information around us. So first I'm going to introduce a little bit about how I did my project. My amazing PI, Dr. Tatiana Sharpie, developed an algorithm called Maximally Informative Dimensions. And it uses rigorous statistical analysis to try to figure out what aspects of what features of a stimulus are instrumental to creating a response. And then that algorithm was further developed by my mentor, Dr. Ryan Rokamp, to not only find one informative dimension, but find multiple. So I've been saying dimension and things like that a lot, so I'm going to explain that a little bit. So finding the information of a neuron is a lot like trying to separate apples and oranges in a fruit basket. If you try to separate apples and oranges by weight, you're not going to get very far because they weigh about the same. However, if you start separating them by color, it's going to be a lot simpler. A still better way to separate them is by a combination of features, not just one feature. So say you want to separate them by color and texture. Then you're going to have a more effective, more efficient sorting. The algorithm works very similarly. Let's say that green points are points that elicit a response, and yellow points represent stimuli that don't elicit a response. What MID is going to do is it's going to plot a trial vector, and then it's going to collapse all of the points onto that trial vector. Then it's going to plot the distribution. As you can see, this distribution, the distribution between the green distribution is not that different from the yellow distribution. This means that we don't really know what makes the green stimuli elicit a response and the yellow stimuli not elicit a response. So the algorithm is going to look at this and say, well, that's not good enough. So it's going to plot another trial vector, then collapse the points onto this one. As you can see, there's a clear difference between the green distribution and the yellow distribution, meaning that we can now draw some sort of conclusions as to what it was about the stimulus that elicited a response. So why do we use this specific algorithm? The maximally informative dimensions algorithm is unique because it can take in non-Gaussian stimuli. Non-Gaussian stimuli are simply stimuli that aren't normally distributed. An example of a stimulus that is normally distributed is like radio static or TV static. And the reason why we need to study things that aren't normally distributed is because things that are normally distributed don't stimulate certain areas of the brain. Since I'm working with auditory data, I'm working with higher level auditory processing areas that aren't stimulated by the noise that follows a normal distribution. Now I'm going to teach you a little bit about my project. So my project started out as research at the University of Pennsylvania, where they recorded natural sounds and scenes and then played them back for rhesus macaque monkeys, and they recorded their electrophysiological data. The results, the data was taken from two auditory areas. The first is called the superior temporal gyrus. The second is called the prefrontal cortex. So traditionally, the prefrontal cortex is considered the higher level processing area, and the superior temporal gyrus is also a high level auditory area, but it's considered to be lower on the hierarchy. My question that I was trying to answer this summer was, which type of neuron is more complex? So are the prefrontal cortex neurons or the superior temporal gyrus neurons more complex? And complexity, for my purposes, is defined as how many features are needed to explain the response. So my experiment went as follows. I received stimuli files and response files. I ran them through our algorithm, Maximally Informative Dimensions, and then using the information values that were calculated, I was then able to determine which type of neuron is more complex. So last summer, I worked in the same lab, and it took me most of the summer to acquire just the very, very basic to start being able to look at my stimulus. This summer, however, after continuing effort, I was actually able to get results, which is pretty amazing. So this is a graph that represents the information provided by the first feature. And in this graph, the orange represents the superior temporal gyrus neurons, and the blue represents the prefrontal cortex neurons. As you can see, the prefrontal cortex neurons are more explained by the first feature than are the superior temporal gyrus neurons. This means that they are more simple because they only need one feature to explain them. This graph shows how much information is gained by adding a second dimension. And in this graph, you can see, again, the superior temporal gyrus neurons, which are represented in orange, they have a larger gain of information when the second feature is added. This means that they are more complex because they're more nonlinear, because more than one feature is needed to explain them. So the potential applications of this research they don't have an end to them, because you can do basically anything. By studying sensory processing, you can then get clues about higher level processing. You can better understand the brain. You can even use it translationally in retinal implants, cochlear implants, and you can understand neurological disorders better. In addition, it can be used to better understand our brain, which is an amazing upcoming field in science. I'd like to thank a lot of people for giving me this experience and making this such a wonderful program for the second summer now. So I'd like to thank my amazing mentor, Dr. Ryan Brokamp, for all of his support, and Dr. Tatiana Sharpie for welcoming me back. I'd like to thank Donna Mabston and Ellen Potter for being here and having us and hosting us, and it's been wonderful. I'd like to thank my wonderful lab. I'd like to thank Chelsea. She helped me with our presentations. I'd like to thank my fellow interns. The second year has been even more fun than the first year. And I'd like to thank LSSI for giving me this opportunity. Thank you.